These are your 3-3 notes on linear programming. This section will build upon what we did in the previous section where we graphed linear inequalities, a system, and it's sort of the brand new part to systems that we did not do in Algebra 1 or geometry. So linear programming is a procedure used to find the maximum and minimum values of a function. I'm going to go over a real life problem in class after these notes, but right now we're just going to do the basics and understand the vocab and what it means. I'll apply it to a real world problem where you would use linear programming afterward. I think it makes more sense when you have that real life example. There are 3 parts to linear programming. There's the parts called the constraints. Those are your lines that you graph of the inequality, and they're called the boundary lines. The feasible region, that's the shaded area where all of the graphs intersect. And then the table of values. The table of values you use when you're calculating the possible combinations of x, y to obtain the maximum or minimum values of the function. So really quick, I can just show you a picture, an illustration of each of those things. So on a coordinate plane, let's say I have 3 different lines coming together, and where the graphed region or the shaded region is inside there. These are considered the constraints. This region right here where all of those shadings come together, this is called the feasible region, and what that means is the answers can only come out of there. That's the region where all the feasible answers are. Any other ordered pair that does not belong in that shaded region will not be answers. And then your table of values you use to collect the minimum and maximum values. You simply take these vertices, make a table of values, and you use those ordered pairs. You plug them into a function, and you'll get values. Within those values, one of them will be the biggest value, called the maximum, and the smallest value will be considered the minimum value. So let's go ahead and try this. We're going to find the maximum and minimum values of the function below. So this is the thing that we're trying to maximize or minimize. There's no story that goes along with it, but a lot of times in life we try to maximize money and we try to minimize cost. So a lot of things in life that deal with linear programming would involve maximizing cost or space, and then minimizing would be cost or materials or time. Maybe you want to minimize your time, and so that it is more efficient. The equations here are the inequalities. These are our constraints. So we're going to graph those 4 constraints. We're going to figure out where they crisscross all the solutions, and that will be our feasible region. So we're not going to do anything with the function until the very end. So the very first thing we have to do is just graph these 4 constraints. X less than or equal to 6 is a vertical line at 6. It's solid, and just to refer to the graphs, all of them are going to be solid because all of them have an equal to sign underneath the inequality. Less than 6, I would use a point like 0, 0 to check. When I check using 0, 0, 0 less than 6 is true. So I'm going to shade to the left. I'm going to use my little dotted lines to tell me that I'm talking to the left of that first constraint. Y less than or equal to 3 is a horizontal line at 3. It is also solid. Pick a point now on the line. I'm going to use 0, 0 again. Is 0 less than or equal to 3? This is true. 0 is less than or equal to 3. So we're going to shade below that line. So I'm going to shade below that line, and I can stop right when I get to the 6th line. So now I'm below the 3 and to the left of 6. The next equation actually has a slope. So before I can graph this, I need to put it in the right order. X minus 3y equals 9. I'd subtract x. Negative 3y equals negative x plus 9. And if I divide by negative 3, I get 1/3 x minus 3. So I'm going to graph that constraint starting at -3 on the y-axis, and then my slope is a positive 1/3. So that means up 1, 3 to the right, up 1, 3 to the right. We connect and extend, and then pick a point not on it. I can use 0, 0. 0, 0 is above it. So when I plug 0, 0 in, I get 0 less than or equal to 9. Is that true? Yes. So I'm going to shade above this line, but I'm only going to work right up to that line 6 again. So right now you can kind of see the area where they're all going to come together. And the last line is already in slope-intercept form, y greater than or equal to -5x plus 8. So I'm going to go up 8. And then I'm going to use a slope of -5. So that means I work down 5 over 1. Down 5 over 1. Now I have to decide where is the shading going to be. Okay, it could actually be in a couple different areas. And so I don't really know for sure. You got to make sure you actually do the check. So I'm going to use 0, 0 again to check. Is 0 greater than or equal to 8? That is false. So 0, 0 was below this line, so I'm going to shade above this line, so it's this region right here. And so you can see it's that little box, that little trapezoid type shape, that quadrilateral in between them. So you want to shade the feasible region. We always shade the feasible region. And what that means, again, is this is the only area that will work for all 4 constraints. So any feasible answers will come out of that area. And so when you're trying to find the maximum value and the minimum value, these are the only ordered pairs that you can plug into the function. But in linear programming, what we've discovered mathematically, you can plug in as many ordered pairs as you want, any combination of the millions and infinite supply of ordered pairs in here. But something has happened in linear programming that says your biggest number and your smallest number of a function will be found at these vertices. So we don't have to waste time plugging in all of those values inside the feasible region. We simply just take the vertices of the feasible region and only use those 4 values. Now in this particular case, we had 4 values to try. Other feasible regions may only have 3. Some may only have 2. So let's go ahead and write down our ordered pairs for each of these. So the first ordered pair is 1, 2 up here. The next ordered pair is 1, 2, 3, 4, 5, 6, 3. This other one is 6, -1. And it looks like we have 2, -2. So it's really important that we graph with accuracy here and we really have the right ordered pairs of your feasible region. Otherwise, you're not plugging in the right points. So now I'm going to make this function turn into a table of values. Very similar to how we use a t-table for graphing. We plug in an x and we get a y. Only this time, we're going to plug in an x and a y, and we're going to get a value for the function. So I'm going to plug in 1, 2. I'm going to plug in 6, 3. 2, -2, and 6, -1. So when I plug these values in, what it really means is I am going to take 3 times 1, add it to 4 times 2, and that actually gives me 11 for my value of that function. When I plug in 6, 3, that's going to be 3 times 6 plus 4 times 3. I can use my calculator. 3 times 6 is 18. 4 times 3 is 12. That gives me 30. 2 and -2 is 3 times -2, plugging in the x value. Oh, sorry. Plug in +2. 3 times +2 plus 4 times -2. That's 6 minus 8 is -2. And then the last one for 6, -1, that would be 3 times 6, which is 18, plus 4 times -1, which is -4. So 18 minus 4 is 14. Once we've collected all that information, we were actually trying to figure out the maximum value of this function and the minimum value of this function. And so the maximum value is 30. So my maximum value is 30 because that was the highest amount we got when we plugged in our vertices of our feasible region. The smallest value that this function will give with these constraints is -2. So you just make a table of values and you pick out the biggest one, that's your maximum, and you take the smallest one, that's your minimum. Let's try one more. So in this one, we got to do a little bit of work. So that first equation here, or inequality, looks like 2x plus y is greater than or equal to 3. I'm going to subtract 2x from both sides to get it in terms of y equals something. Y equals -2x plus 3. So I'm going to go up 3, and my slope is down 2 over 1. I just carry my slope a little bit further here because I never know. I need to be accurate on my point, so I want to make sure that it truly is straight. It is solid. All of these are going to be solid. In fact, in all linear programming, they have to be solid in order to use the vertices. So I'm going to pick a point not on it, like 0, 0. When I plug 0 in here to check, I get 0 greater than or equal to 3. That is false. 0 is not greater than 3, so I'm going to shade on the opposite side. So I have my dotted lines above that graph. Second equation, I'm just going to move down here so I have some room. 3y minus x equals 9. Make yourself room to do your adjusting. This seems to be a problem area. So we get 3y is equal to x plus 9. We need to divide by 3 so we can get our slope and our y-intercept. Y equals 1/3 x plus 3. So I'm going to start at positive 3 again. And a slope of 1/3 means to go up 1, 3 to the right, up 1, 3 to the right, or down 1, 3 to the left. Pick a point not on it. 0, 0 works. So I plug 0, 0 into the original. I get 0 less than or equal to 9. That is true. So I'm going to actually shade where 0, 0 is, which is below. But I want to make sure that I stay to the right of that other line. Next one, y equals, if I subtract that 2x over, I get y equals -2x plus 10. So we're going to start up at 10, which is at the very top of my graph. I'm going to go down 2 over 1 each time. Down 2 over 1, down 2 over 1. This is actually going to be as parallel to the other line because they both had a -2 slope. When I pick a point not on it, 0, 0 is below it. I plug it in. 0 less than or equal to 10 is what I'm asking. That's true. So I'm going to be below this line. So I'm only going to shade this region right here. So right now we've got this rectangle below that other line in between those two parallel lines. Last constraint is a horizontal line at -4. So I have a horizontal line at y greater than -4 or equal to. When I plug in 0, 0 to check for shading, 0 greater than or equal to -4 is true. So I'm going to shade above that line, in between the parallel lines, and now you can see our feasible region. So the feasible region here is everything where we had the crisscrossing of our shading. These are the only numbers that satisfy all the constraints. The ordered pairs in here will make every single one of those ordered pairs, the constraints true. Now we're going to refer to the function, and I want to evaluate the function f of xy for the value of 5x plus 4y. I want to find the minimum and the maximum. So I need these ordered pairs. I've got 0, 3. I've got 1, 2, 3, 4. And looks like 3, -4. And this last ordered pair is 1, 2, 3, 4, 5, 6, 7, 8, 8, -4. So I'm going to use those ordered pairs, plug them in, 0, 3, 3, -4, 8, -4, and my last one was 3, 4. And this one didn't come out right, so that's a 0, 3. So when I plug those in, 5 times 0 plus 4 times 3 gives me 12. 5 times 3 is 15, plus 4 times -4 is -16, gives me -1. 5 times 8 is 40, plus 4 times -4 is 16. So 40 take away 16 is 24. And 5 times 3 plus 4 times 4, that's 15 plus 16 is 31. So in this case, the maximum value is 31 and my minimum value is -1. Biggest number, smallest number. The other two numbers are just there to help you understand which one's the biggest and which one's the smallest. So that is linear programming. So I have this picture here of this graph because it's going to apply to both questions. In the lesson summary, I want you to name the coordinates of the feasible region. So give me the vertices. And then using those vertices, I want you to actually figure out the maximum and minimum values using that function. F of xy is equal to 2x minus 1, and that should be actually minus 1y. There should be a y there. All right, good luck.